Welcome to This Explainer. I am so thrilled you're joining me today because we're tackling one of the most fascinating, mind-bending subjects in materials engineering. Did you know that if you stir certain liquid plastics, they don't just swirl around like normal liquids, they will actually climb straight up the stirring rod, completely defying gravity? Yeah, it's called the Weissenberg effect, and it perfectly sets the stage for what we are doing today. Our main goal here is to really understand the phenomena and mechanical properties of polymer solutions and molten plastics. We want to master the physical properties and figure out how to mathematically represent these basic flow types. If you've ever wondered how engineers design all the complex plastic parts that make up our modern world, the secret lies entirely in how these materials behave as fluids. It's a world where standard physics just gets turned completely on its head.
Okay, let's dive into this. Here's a quick roadmap for our journey today. First, the nature of polymer flow. Second, molecular structure and viscoelasticity. Third, mathematical models of flow. Fourth, transport phenomena and equations. And finally, measuring flow with rheometry devices. We're going to logically progress from observable macro behaviors all the way down to complex math and real-world testing.
Part 1. The nature of polymer flow. Let's look at why plastics defy standard physics. To put it simply, when you melt a polymer down so that it flows, it absolutely does not behave like the fluids we interact with every single day. To really grasp this, we have to contrast polymer melts with simple liquids. Think about a standard Newtonian fluid, like a glass of water. If you stir that water, its viscosity, its resistance to flow, stays completely constant regardless of how fast you stir it. But polymer melts? They're not Newtonian. Specifically, they exhibit something called shear thinning. That means their viscosity is highly variable. The faster you deform or shear the material, the thinner or less viscous it gets. It's actually a lot like trying to get ketchup out of a glass bottle. You smack the bottle to apply sheer force, and suddenly it thins out and flows everywhere. This variable viscosity sets up the fundamental puzzle of our explainer. How on earth do we predict and control a fluid that changes its thickness based on how we treat it? And this brilliantly illustrates exactly what we're talking about. Take a look at this curve showing viscosity against shear rate. Over at the very low shear rates, the polymer maintains a constant high viscosity. We call that the first Newtonian plateau. But as the deformation rate increases in that middle section, wow, look at that steep drop. The bulk viscosity of the melt just plummets. That is our shear thinning region. Finally, at extremely high shear rates, it levels off again at a much lower constant viscosity, known as the second Newtonian plateau. Understanding this specific curve is absolutely paramount for anyone working with plastics. Part 2. Molecular structure and viscoelasticity. Let's look at the architecture of flow. So we've seen the macro behavior of the fluid, but to truly understand it, we need to zoom in on the micro-level molecular architecture that actually causes it. Notice the molecular structure of these different polyethylenes: high density, low density, and linear low density. I want you to think of polymer molecules like a giant tangled bowl of spaghetti. These are incredibly long molecular chains. Notice how some, like PLD right in the middle, have these long, tangled branches. When the material is at rest, those branches are completely entangled with one another. But when we apply a high rate of deformation, when we stir the pot, so to speak, these long molecular chains actually untangle, they stretch out, and they align with the flow. Because they're stretched out, they can slide past one another with so much more ease. That structural realignment under stress, that is exactly what causes the shear thinning we just saw. This brings us to a really critical definition: viscoelasticity. Because of those long tangled chains, polymers aren't purely liquid and they aren't purely solid either. They are viscoelastic. This means they exhibit both liquid-like viscous flow and solid-like elastic recovery. And here is the kicker. Which behavior dominates depends entirely on the time scale or the speed at which the molecules are deformed. Think of it exactly like silly putty. If you pull silly putty slowly, it stretches and flows like a thick liquid. But if you snap it quickly, it breaks. Or if you roll it into a ball and drop it, it bounces, just like a solid rubber ball. This dual personality is exactly why the math we are about to see gets quite complicated. Part 3. Mathematical models of flow. Calculating the movements. We've seen the behavior and the molecular cause. So the crucial point is how we actually calculate these movements and mathematically represent these basic flow types. To visually anchor the upcoming equations, let's look at the two most fundamental types of flow we model. Up top, we have Puzel flow. This is flow driven by a pressure difference, like forcing molten plastic through a cylindrical tube or a pipe. Notice that curved velocity profile. The fluid is moving fastest right in the center. Below that, we have couette flow. This is a simple shear flow driven by a moving surface, like fluid trapped between a stationary bottom plate and a moving top plate. Here, the velocity profile is just a straight line. I want to emphasize this heavily. Every complex polymer process out there is essentially a combination of these two basic flow types. They are the foundational building blocks of the entire discipline. So how do we model that variable viscosity mathematically? Engineers use the generalized Newtonian fluid, or GNF model. Let's break this down piece by piece. In standard Newtonian math, viscosity is a constant. Easy. But in the GNF model, our non-Newtonian viscosity is an entire function. Because polymer melts essentially can't be compressed, the complex math simplifies just a bit. What you really need to take away from this is that the non-Newtonian viscosity relies on something called the second invariant of the strain rate tensor. Now, I know that sounds intimidating, but it's really just a fancy mathematical way of measuring the shear magnitude of the deformation. By tying viscosity directly to this strain rate magnitude, the math remains digestible while accurately reflecting the real-world shear thinning.
Part 4, Transport Phenomena and Equations, Modeling the System.
Before we dive into the heavy lifting physics equations, I want to tie this to real-world stakes. Look at this diagram of an injection molding system. You've got molten plastic in a reservoir, being forced under immense pressure through a narrow sprue, branching into runners, and squeezing through a tiny gate into the mold cavity. The shear rates and temperature changes happening here are extreme. If our fluid mechanics and rheology calculations are wrong, if we misunderstand the transport phenomena, that manufactured plastic part will warp, break, or just fail to fill the mold completely. The math literally dictates manufacturing success.
To prevent those costly manufacturing failures, we rely on the Navier-Stokes equations, which essentially balance the forces, mass, and momentum in the fluid. Here you see the breakdown of these equations across cylindrical coordinates, radius, angle, and length. In standard fluid mechanics, these are tricky enough. But for polymers, these equations become highly nonlinear. Why? Because as we've learned, the viscosity term isn't a constant number. It is constantly changing depending on the rate of deformation, the temperature, and sometimes even the time elapsed. Solving these nonlinear partial differential equations is pretty much the ultimate challenge in polymer physics.
Part 5, Measuring Flow, Rheometry Devices. If our mathematical models require precise viscosity data to actually work, how do scientists capture that data to plug into those complex equations? The answer is rheometry. Now, what's really interesting about this slide is how the physical geometry of these testing devices directly links to the math we just covered. On the left, we have the cone and plate rheometer. Because of the cone's specific angle, the shear rate is totally uniform throughout the entire sample. It's mathematically beautiful. On the right, we have the parallel disc rheometer. Here, the shear rate is not uniform. It varies from 0 at the center to a maximum at the outer edge. While the parallel disk is great for certain linear studies, that non-uniform shear makes it unsuitable for complex nonlinear mathematical modeling.
Next up is the concentric cylinder, originally invented all the way back in 1890. This device uses a rapidly rotating outer cylinder and a stationary inner cylinder. The fluid just sits in the tiny gap between them. Because the gap is so small relative to the radius, this device achieves a nearly constant shear rate across the fluid. It's incredibly exciting that century-old tech perfectly models that moving surface couette flow we saw earlier. This allows us to accurately measure the torque today and calculate the precise viscosity of the liquid. So which device do we use when? Let's do a rapid-fire summary. Cone and plate devices are fantastic because they require very small sample sizes, like 1 gram, they're easy to clean, and they provide that coveted uniform shear rate. Concentric cylinders? Great for uniform shear, but they require massive sample sizes up to 30 grams and are a nightmare for loading highly viscous melts. Sliding plate rheometers give you incredibly simple mathematical equations, but they're notoriously difficult to load and clean in a lab setting. The choice always depends entirely on the specific mathematical model you're trying to populate with data.
Which leaves us with one final provocative question. We know polymers are nonlinear, viscoelastic, and incredibly complex to model. Today, we use computational fluid dynamics, or CFD, to simulate these flows digitally. But as our mathematical models for molecular entanglement become even more advanced, how will tomorrow's supercomputers solve these massive nonlinear equations? The application of CFD is poised to entirely change the way we manufacture polymer products, allowing us to literally design the impossible plastics of the future. Thank you so much for joining me on this deep dive into the physics of plastic. Keep exploring, keep learning, and I'll catch you in the next explainer.